All right, we're going to look at Venn diagrams. And in particular, first of all, we're going to take a look at the union and intersection of sets and how they can be displayed with Venn diagrams. So first of all, let's look a little bit of set notation, right? We have here the symbol here is the union of two sets. And this symbol here is the intersection of two sets. Right, the intersection of two sets. And when we say the union of two sets, what we're talking about is when we're talking about does an event or an item appear in two sets, we're saying that it appears in either A or B. We don't care which one it appears in, but it just appears in one or the other. Right? When we're looking at the intersection of two sets, we're saying that an item appears in A and B. So it appears in both sets. And this will become clearer when we actually look at the Venn diagram. So Venn diagrams are just ways of displaying how items appear within sets. So if we look first of all at the set A and the set B, and we look at the union of those two sets, A union B, right? So A union B here is both of the sets put together, right? Both of the sets put together. You can see the crossover between the two right here in the middle, right? One of the things we've got to be careful with when we deal with the addition rule later on is that we don't count this twice. All right, so we've got to be careful with that, right? So the second thing we're going to look at here is we're going to look at the intersection of two sets. So once again, using Venn diagrams, using circles, each circle representing a set, right? This circle representing set A, this circle representing set B. We can then look at the intersection of two sets. So A intersection B being just the middle, just the part right here in the middle. Okay, so any item in A and B, or an A intersection of B, we can show that it appears in both sets. Okay, so moving on to a few examples on how this relates. Let's take a look at this spinner here and how we might actually display this in a Venn diagram. So we've got a spinner here. Our sample space is all the numbers 1 through 8. So each of these numbers has to appear in our sample space S, which is inside this box, right? We're also being given two events. Event A landing on an even number, and we're going to use this circle here to signify the set of event A, all those even numbers, and this circle here to signify the set of event B, which is all the prime numbers landing on a prime number, right? So we'll see what they have in common as well. So first of all, let's set up the sets, right? We've got to go through every single number here. So first of all, set A, right? So set A is the even numbers, so 2, 4, 6, and 8. So set A is 2, 4, 6, and 8. And set B is the prime numbers. Well, 1 is not prime. 2 is prime, right? It only has 2 factors. 3 is prime, 5 is prime, and 7 is prime. Okay, so we've set up our two sets. So now let's start placing it into the Venn diagram. Okay, the first thing that you should do is take a look at both sets and see which numbers they have in common. We see here that the 2 is in common for both. So we're going to put that in the middle because that appears in both sets. So therefore, that item is in A and it's in B. All right. So the rest of A is 4, 6, and 8. So we'll put that in 4, 6, and 8 in A. They don't also appear in B. And set B is 2, 3, 5, and 7. Now we note we haven't used 1, so we do need to put 1 out here in the sample space, and we've accounted for every number: 1, 2, 3, 4, 5, 6, 7, and 8. All right, perfect. That's how you set it up. Okay. Now the question is, what numbers are in set A union B? Well, that's all these numbers within the whole set. So you get 2, 3, 4, 5, 6, 7, and 8. So A union B is equal to the set 2, 3, 4, 5, 6, 7, and 8. And in A intersection B, we'll see that we've only have right here in the middle, we've got just a set with a 1 item, and that's 2. All right, so that's the beginning. That's kind of just looking at setting up setting up from the spinner what goes on there. Okay, so we've set up our sets, we've set up our union, we've set up our intersection. We hopefully understand roughly what's going on there. Let's look at how that deals with probability. Okay, so I'm going to kind of rewrite a few things real quick. I'm going to hide the Venn diagram and rewrite the sets real quick, so we can actually take a look at these. So this was here. This set was 2, 4, 6, and 8. This was 2, 3, 5, and 7. And we had the A union B was the set 2, 3, 4, 5, 6, 7, and 8. And A intersection B was 2. Right, so that's where we left off. Now, we have this strange notation here, the number of items, and we looked at this in a previous lesson. So the number of items in A union B, if we count them as 1, 2, 3, 4, 5, 6, 7, right? And we've got the number of items in A is 4, and the number of items in B is also 4, okay? So why is A union B not equal to 4 plus 4? Right, you would assume that maybe it is, but like I mentioned at the beginning of the video, right, we have to make sure we don't count both twice. So why is this not true? In doing so, we're actually counting one item twice. There's an item that appears twice in here, and we're counting it twice if we just add it together. So we are counting the intersection twice, right? So the intersection is only one item. So to do that, we'd subtract the number of items in A intersection B, and that's how that works, right? So that will lead us to the addition rule. Let's take a look at the addition rule. Before we do, we're going to look at a few quick examples, right? Including probability. So the probability that a randomly selected student prefers dogs, pause and read this if you like. So prefers dogs, we're looking at, well, we've got 56 students prefer dogs out of 100, so that's going to be 56 out of 100. The probability that a student prefers dogs or prefers cats, well, that's going to be 56 plus 36 out of 100, right? So we got 56 out of 100 plus 36 out of 100, right? So that's going to be 92 out of 100, right? So we get 92 students that out of 100 that prefer dogs or prefer cats, right? Okay, so notice that there's no intersection. You can't prefer dogs and prefer cats. So we don't have to worry about subtracting the intersection just yet, okay? Like we had to do in the previous example. So all we got to do is add them together, right? Let's continue, right? Take a look at another probability, right? So what about the probability that a randomly selected student prefers dogs or is female? So again, we're going to take the prefers dogs or is female, right? All right, so we've got 56 out of 100 prefer dogs, and we got 52 out of 100 are female. But notice, if you're really careful, if you notice this here, what we're actually counting here is we're counting all of these people here, right? These are preferring dogs or being female, is what we're counting. Okay, and what if we just add up this total and this total, then we're counting this 20 twice. So we need to subtract the 20 to make this work, right? And what we'll find is we'll have 88 out of 100, or 88%, right? So the key idea here is you need to subtract the intersection, and if you add each of these up, 36 plus 20 plus 26 plus 6, you'll get yourself 88. Okay, so that leads me straight to the addition rule, and here is the addition rule. The addition rule accounts for this by subtracting the intersection. When you do the probability of A or B, of event A or B happening, is equal to the sum of the two probabilities, so minus the intersection. This is always true. For mutually exclusive events, which we're going to talk about later, we don't need to worry about the A or B, and in fact that kind of helps us to test for mutually exclusive, or the A intersection B, because that's going to always be 0, right? But the addition rule here will work for every situation. So I'm going to leave it at that.